Topic 6.7, graphing linear relations. A linear relation can be graphed. And when you plot the points on a coordinate grid and connect those points, you will find that they form a straight line. And that's actually why the type of relation is a linear relation, because it makes a line. So now let's take this problem and we'll do just that. We'll create a table of values and we will graph those values. Sylvia is paid $6 for every tray of tomatoes she plants. Let's let N represent the number of trays she plants and let P represent her pay in dollars. An equation that relates her pay to the number of trays she plants is P is equal to 6N. Substitute values for N to find corresponding values of P. What if N is 0, 1, 2, 3, 4, or 5? Now graph the linear relationship. Here's a table of values with the letter N as the input column and the letter P as the output column. Now remember, N is the number of trees that Sylvia plants, the number of trees, and P is her pay. All right, so her pay is dependent on the number of trees that she plants. And the relation we were given in the problem is that her pay is equal to 6, representing dollars, times the number of trees she plants. Okay, so in other words, $6 per tree she plants. So now, if she plants 0 trees, of course she's going to make no money. 6 times 0, if N were 0, would be 0. If she planted 1 tree, you substitute the 1 in here in place of the N. 6 times 1 would be 6. If N is 2, that is, she planted 2 trees, 6 times 2 would be 12. Okay, and so it goes. Remember that this relation here, this pattern, rather, continues. So if it's plus 6 for every tree, this should be 18, plus 6, 24, plus 6 is 30. Of course, we can double check those answers as well, right? So 5 times 6 is 30, so that is a correct answer. Now, if we have a look at our table of values, we actually have a series of pairs of numbers. And each one of those pairs, for example, this one here, is called an ordered pair. And it's called an ordered pair because there's a special order to it. The first number represents the input. In this case, it's the number of trees. And the second column represents the output. And in this case, that's the pay in dollars. And these ordered pairs can also be interpreted as coordinates on a grid, like you see here. So I've set up a grid here with N on the bottom, on the x-axis here, and I've numbered them up to here, all the way up to 8 trees. And on the y-axis, I've drawn a P over here. This is the output axis, and that's the pay. So I've gone up in increments of $6. She gets paid $6 for every tree she plants. Now, these coordinates, these ordered pairs, can be graphed. They can be plotted and they can be graphed. So let's try plotting the first one, 0 and 0. So when N is 0, her pay is 0. So I've put a little dot here where these two axes meet, and that represents the first ordered pair. Next we've got 1 and 6. So when N is 1, her pay is 6. So we'll put a point here representing that point. How about 2 and 12? So 2 and 12. When N is equal to 2, she makes $12. And so on. So 3 and 18. 3 and 18 would be here. 4 and 24 would be here. 5 and 30 would be about here. Okay? Now, the neat thing about a linear relation is that when you graph the relation itself, it forms a straight line. Now, these dots, when connected, will form a perfectly straight line. Now, the neat thing about understanding a linear relation and how an ordered pair, like let's say 5 and 30, actually works, is that if you're given one of those values, you can find the other one. So for example, let's say Sylvia can plant trees really, really quickly, and she plants 80 trees in a day. How much money is she going to make in that day? Well, if n is the number of trees, and she plants 80 trees, then we have a problem like this. How much money does she get? We can replace that with a variable, of course. So let's say P for pay, right? Well, if our relation is that P is equal to 6n, and we understand this relation, then all we need to do is plug in this value for n, and we can determine what her pay would be. So in this case, her pay would equal 6 times 80, which would be $480 is what she'd make if she was able to plant 80 trees in a day. What if we knew the amount of money she made and we wanted to find out how many trees she was able to plant in the day? Well, let's say that we knew that she made $72 one day, and we want to know how many trees she planted. Well, because these two numbers are related to one another, we can still use this same relation to determine the value of n. So in this case, we would plug the 72 in instead of the p. So that's how much money she made, that's her pay. And then we would solve for n. So we have a basic algebra problem here. We divide by the coefficient, do the same on this side, and you'd find that she planted 12 trees. Let's try some more examples. Create a table of values for integer values of x from 0 to 5, and then graph the relation. A table of values has an input value and an output value, okay? And these two values are related to one another in this relation. Y is equal to 3x plus 1. Now the instructions tell us to create a table of values for integer values of x from 0 to 5. So what we're going to do is figure out what y would be, what the output would be, when x is equal to 0, and then 1, 2, 3, 4, and 5 as well. So when x is equal to 0, well, anything times 0 is 0. So 3 zeros would be 0, plus 1 would be 1. So all I did is I substituted the 0 for the x here, and I solved for y. Now what if x is equal to 1? Well, this x would be replaced with a 1. 3 times 1 is 3. 3 plus 1 is 4. So when x is 1, y is equal to 4. How about when x is 2? Well, 3 times 2 is 6, plus 1 is 7. Okay, now at this point, we should be catching on to the pattern here. Looks like we're adding 3. So because it's a linear relation, that pattern is going to continue. So this number should be 10. 7 plus 3 is 10. This should be 13, and this should be 16. Now remember that each one of these pairs of numbers is actually an ordered pair. And the order is x, y. X first, then y. Now, these can actually serve as the coordinates of a point on a grid like this. So that enables us to graph a linear relation on an xy grid. So when x is 0, y is 1. This is the x-axis, and this is the y-axis. So when x is 0, y is 1. That would be the first point. When x is 1, y is 4. So x is 1, y is 4. When x is 2, y is 7. 2 and 7. When x is 3, y is 10. Okay? And if we continued this, of course, the other points would be up here. Now we can connect these points, and when we connect them, we'll find that they actually make a straight line. How about number 2? Y is equal to negative 3x minus 1. So let's start by creating our table of values. And we will list the numbers 0 to 5, x values 0 to 5. And then we're going to determine what y would equal in each of these cases. So when x is at 0, negative 3 times 0 would be 0. 0 minus 1 would be negative 1. So when x is 0, y would be negative 1. When x is 1, let's substitute 1 in here. Negative 3 times 1 would be negative 3. And negative 3 minus 1 would be negative 4. Okay, how about when x is equal to 2? Well, negative 3 times 2 is negative 6. Negative 6 minus 1 is negative 7. All right, so once we've got 2 or 3 of these, we can have a quick look and see what the relation is. It looks like we're subtracting or decreasing the value by 3 every time. So if we continue doing that, we should be able to plug in those values. That's the really neat thing about linear relations, is once we know a few of those ordered pairs, those coordinates, and we determine the pattern, we can actually predict the others. So 3 should be negative 10, 4 should be negative 13, and 5 should be negative 16. Now let's plot these coordinates onto our grid and graph the relation. So when x is 0, y is negative 1. X is 0, y is negative 1. When x is 1, y is negative 4. When x is 2, y is negative 7. When x is 3, y is negative 10. It's helpful to use an XY template like this. Makes it quicker and easier to graph. If you don't have one accessible though, graph paper will have to do, and you can just draw your own XY grid. So now let's connect those dots and see our line.